Hello everyone, I am Rikarya Das, third year undergrad student in Department of Electrical Engineering, IIT KPG. We are proud to introduce our project Bit Serial Neural Computation Engine without DSP units. So this project achieved a significant milestone by winning the Gold Award in AI/ML powered FPGA Design and Simulation Hackathon held at NIT Jamshedpur under the Industry Academia Conclave in collaboration with VLSI for All. We would like to express our special gratitude to our mentors and judges whose guidance played a crucial role in shaping our approach and refining our design. We also extend our thanks to Mr. Rajat Kumar Singh, founder of VLSI for All, for his vision and leadership. This platform gave us the opportunity to learn, experiment, and compete at an industry relevant level. Thank you. Let's get started. Okay, so let's try to understand what problem does this project solve. Modern neural networks rely heavily on multiply accumulate operations, and in conventional hardware, these are executed using DSP slices. So what are DSP slices? A DSP slice in an FPGA is a dedicated hardware block optimized to perform high-speed arithmetic operations, mainly multiply and accumulate. DSP slices provide a pre-designed pipeline data path that runs very fast and efficiently. While this works well in GPUs and high-end accelerators, it creates a serious problem when we move to edge devices, FPGAs with limited DSPs or low-powered embedded systems. DSP blocks are expensive in terms of area and power. They are available in limited number on most FPGAs. As neural networks scale, the demand for parallel MAC operations quickly exceed the available DSP resources, forcing designers to either reduce parallelism, lower performance, or move to larger and more expensive devices. This project addresses that exact limitation. Instead of relying on DSP or MAC units, the bit serial neural computation engine performs multiplication using simple logic elements, mainly adders, shifters, and registers. By processing data one bit at a time, the engine trades off some latency for massive savings in hardware resources. This approach solves three key problems simultaneously. First, it eliminates dependency on DSP blocks, making the design portable across low-cost FPGAs and even ASICs. Second, it significantly reduces power consumption because simple logic toggles far less than wide parallel multipliers. And third, it allows scalable precision. We can change the bit width of computation without redesigning the hardware, which is extremely useful for neural networks that tolerate reduced precision. Before going into the architecture, let's get some idea about what is a perceptron. At the most fundamental level, a perceptron is the simplest form of neural network. It takes multiple inputs, multiplies each input by a corresponding weight, adds them together, and then applies an activation function to produce an output. Mathematically, this is just a weighted sum followed by a non-linearity. But from a hardware perspective, this is important because it translates directly into multiply accumulate operations, which dominate the computation costs of neural network. A single perceptron can only solve linearly separable problems. So on its own, it's quite limited. However, when we stack multiple perceptrons together, we get something much more powerful. Now that we understand the perceptron, it's time to clarify that this project is not designed to perform full end-to-end classification. Instead, it is used as a feature extractor, meaning it transforms raw input data into a compact and meaningful feature representation that can later be consumed by a classifier or another processing stage. The idea is simple. Early layers of neural network are responsible for extracting useful patterns such as edges, correlations, and signal structures, while later layers focus on decision making. My architecture focuses on efficiently accelerating this feature extraction stage, which is the most computation heavy part. Before jumping straight into the architecture, just a quick heads up. These slides are a bit old. Since then, we have integrated AXI stream interface into the model, so that part isn't fully reflected here. Don't worry though, the latest and complete implementation is available in our GitHub repository, and you'll find the link shared on the last slide. You can check out the updated code there for full picture. Now let's discuss about the high-level architecture. Our architecture implements a complete AXI stream connected neural network hidden layer computation engine on FPGA, integrating input buffering, weight memory, a bit serial MAC engine, ReLU activation, and proper back pressure handling in the clean streaming architecture. You might be thinking, what is an AXI stream? The AXI stream is the data highway for our engine. Input features stream in through AXI slave interface. The network processes and outputs flow out through the AXI master interface, all handled automatically with valid and ready signals to keep data moving efficiently without stalling. Input feature vectors are received as a stream and assembled into a complete input vector using internal buffering mechanisms. Once a full vector is available, a dedicated Mac engine performs hidden layer computation by sequentially reading weights from on-chip weight memory and executing multiply accumulate operation using bit serial arithmetic. The Mac engine supports configurable parallelism to balance throughput and area. It also employs handshake-based flow control to support back pressure. The accumulated neuron outputs are passed through ReLU activation unit, and the resulting activations are streamed out with explicit end-of-vector signaling. Global busy signaling and handshake-driven data movement ensure safe synchronization between data loading, computation, and output streaming. Now let's talk about the input buffer module. It acts as an input staging and validation block between a streaming data source and neural network computation engine. It receives input values one at a time from a stream, stores them sequentially in an internal buffer, and assembles them into a complete fixed-sized input vector required by the neural network. The module monitors an end-of-vector marker to ensure that exactly the expected number of inputs is received, and it generates a short vector-ready signal once a full valid vector has been successfully captured. To maintain correct operation, it pauses data capture while downstream computation engine is busy and discards malinformation or incomplete vectors if the stream terminates too early or too late. By enforcing strict input alignment and synchronization, this block ensures that neural network always processes well-formed input vectors, providing reliable and deterministic behavior in the streaming hardware system. The weight memory module implements a hidden layer weight memory for the neural computation engine. It stores all the weights connecting input features to hidden neurons in a structured block RAM and produces dual access, a write interface for programming or updating weights for an external host, and read interface for the Mac engine during computation. Incoming weights are written using a two-dimensional indexing scheme, neuron and input, which is flattened internally into a single memory address for storage. The module pipelines writes to ensure timing correctness and supports synchronous reads, providing the Mac engine with the correct weight value each clock cycle. By handling both storage and access in a predictable and efficient manner, the block ensures that the neural network always receives the right weights for computation, while also allowing safe updates from an external controller without disrupting ongoing calculations. Now we come to the most important module, which is the core computation engine of the neural network accelerator. It implements a bit serial multiply accumulate operation to compute the outputs of the hidden layer neuron. Upon receiving full input vector, the Mac engine sequentially reads the corresponding weights from memory and performs multiplications and accumulations using bit serial approach, which efficiently reduces hardware resources on FPGA. To improve throughput, it supports parallel processing of multiple neurons simultaneously. Intermediate results are accumulated in internal registers with proper handling of signed arithmetic to account for positive and negative values. Once all the input features of all the neurons are processed, the results are streamed out sequentially through AXI compatible interface, with handshake signals ensuring that downstream module ReLU activation are ready to receive the data. Now, before exploring the ReLU activation module, let's understand what are activation functions. So activation functions are fundamental components of neural network which introduce non-linearity into the model, enabling it to learn and represent complex patterns beyond simple linear relationships. Without activation functions, multiple layers of neural network would effectively collapse into a single linear transformation, severely limiting the network's expressive power. Activation functions operate on the output of each neuron and decide whether and to what extent the neuron should be activated. Common activation functions include ReLU, rectified linear unit, that we will use in our module, which output 0 for negative inputs and pass positive values unchanged and is widely used due to its simplicity and hardware efficiency. Sigmoid, which compresses values into a range of 0 to 1 and is often used for probability-like outputs. And tanh, which maps values between -1 and 1, providing strong centering around 0. In hardware accelerators, ReLU is especially popular because it requires minimal logic, making it fast and resource efficient while still providing essential nonlinearity needed for effective neural interference. Following the principle, the final module implements the rectified linear unit activation function as a streaming hardware-friendly processing stage. It receives accumulated results from the Mac engine and applies a simple nonlinearity by suppressing negative values and passing through the positive values unchanged. The design is fully handshake driven, meaning it can automatically pause or resume operations based on the readiness of downstream logic, ensuring no data is lost. Internally, the module registers its output, introducing a single clock latency, which allows the result to be safely held if the next stage is not ready to accept them. So far, I have explained the architecture and the functionality of each module at a conceptual level. Now, I'd like to walk you through the actual code implementation. This will show how these ideas are translated into hardware using System Verilog, how the modules interact, how data flows through the design, and how timing and control are handled in practice. I won't go line by line, but I'll highlight the key sections that bring the architecture to life. So let's begin with the top module, which starts with the line timescale 1ns/1ps. It is a directive which defines the simulation time unit. Then these parameters such as data W, precision, N in, N hidden, and P control the data width, computation precision, network size, and parallelism at compile time. Then all the ports here are declared using logic data type. Signals involved in arithmetic are explicitly marked sign to avoid unintended sign behavior. The input and output interfaces follow the AXI stream convention with tvalid and tready implementing the flow control and tlast marking the packet boundaries. A separate wait-write interface is provided with explicitly sized address signals where ceiling log base 2 is used to compute the minimum required address, and a ternary condition prevents zero width vectors when parameters are set to small values. Internal widths are derived using local param declarations such as accumulator width and packet input vector width. Using local param instead of parameter prevents accidental overrides and keeps internal sizing consistent. Wide data such as full input vector is represented using packed vectors, which are fully synthesizable and allow clean module to module data transfer. Control signals like valid, ready, and busy are explicitly declared, making pipeline flow visible and easier to reason out. Simple combinational control is expressed using continuous assign statements. For example, S-axis T-ready is driven directly from the busy signal to implement AXI back pressure without a state machine, and ready signals are propagated structurally between pipeline stages. This style keeps the control path simple, predictable, and easy for synthesis tool to optimize. Submodules such as the input buffer, wait memory, Mac engine, and ReLU are block instantiated using named port connections. Control between these blocks is handled through valid ready handshakes rather than centralized FSMs, allowing back pressure to naturally propagate upstream. The Mac engine is started using single control pulse derived from input buffer, and its output readiness is directly tied to the readiness of the next stage. Here, sequential logic is written using always FF blocks, which enforce proper clock behavior and prevent accidental mixing of combinational and sequential logic. The output index counter is updated only when valid AXI transfer occurs, and the reset behavior is clearly defined using an active low reset. The use of zero literal ensures width safe assignments using reset, avoiding truncation or extension bugs. AXI T-last generation is implemented using simple combinational logic based on the counter value and valid signal, rather than an explicit state machine. Now, this code implements a input buffering block that collects a stream of incoming data words and assembles them into a fixed length vector under explicit control conditions. Internally, a write pointer tracks where the next incoming word should be stored, and a small memory array is used to hold the intermediate values. The pointer width is derived from configured vehicle length so that indexing is always safe and synthesis friendly. The buffer contents are exposed to the rest of the design in a single wide bus. Instead of building the bus procedurally, the code uses a generate for construct to map each buffer entry to a fixed slice of output vector. This creates purely static wiring, which is easy for synthesis tools to optimize and avoid additional control logic. All the state updates occur on the rising edge of the clock within single sequential block. On reset, the write pointer and buffer contents are cleared and completion indication is deasserted during normal operation. The completion signal is kept low by default and is raised for exactly one cycle only when a full vector has been received. Data is captured only when two conditions are met. The incoming data is marked valid and the downstream logic is not busy. The gating ensures that partial vectors are not overwritten and that the buffer does not accept new data while consumer is still processing previous vector. The pointer advances with each accepted word. The control logic explicitly checks the position of the right pointer against expected vector length and end of vector marker. When the final word arrives, the correct marker, the pointer is reset and completion pulse is generated. If the buffer fills without the marker or if the marker arrives too early, the current contents are discarded by resetting the pointer. These error cases are reported through simulation only messages, allowing protocol violations to be detected during verification without impacting synthesized hardware. The weight module implements a parameterized weight memory for hidden layer, storing all weights in a single flattened memory structure. The parameters define the weight width and the dimensions of the weight matrix, and from these, internal constants are derived to determine the total memory size and required address width. This approach ensures that memory sizing and index scales automatically with design configuration. The memory itself is declared as a synthesizable array and is explicitly annotated with RAM-style block attribute to encourage inference on block RAM and FPGA targets. The storage is one-dimensional even though the weights are conceptually two-dimensional. This simplifies the memory interface and allows both read and write operations to use a single address space. To support safe and timing-friendly writes, the code introduces a small write pipeline. Incoming write data, the flattened address and the write enable are all registered on the clock edge. The flattening operation converts the two-dimensional address formed by hidden neuron index and input feature index into a single linear address. Registering this logic isolates address arithmetic from memory write port, improving timing closure and making the behavior deterministic. The memory access itself is handled in a separate clocked block that models synchronous block RAM behavior. Writes occur when the registered write enable is asserted using registered address and data. Reads are also synchronous, with the read data appearing one clock cycle after the read address is applied. Reset logic initializes the pipeline registers and the read data output to known values, ensuring clean startup behavior. Now coming to the Mac engine, we know it implements multiply accumulate engine using structured combination of control logic, counters and bit serial arithmetic. It is fully parameterized so that data with precision, number of inputs, number of neurons and parallelism are all resolved at compile time. From these parameters, several local constants are derived to size counters accumulators correctly, ensuring the arithmetic growth and indexing remains safe and deterministic. Internally, the design is organized around a small finite state machine with three states: idle, proc, and streaming. The FSM controls when computation begins, when accumulation is active, and when results are sent out. State transitions are driven by explicit conditions such as completion of all input bits, exhaustion of input features, and completion of output streaming. This keeps control flow explicit and easy to trace rather than implicit through nested counters. The core computation is coordinated using several counters that track the current hidden neuron, the current input feature, the current bit position for bit serial processing. Additional flags manage memory read latency and indicate when bit level accumulation is active. Parallelism is handled by indexing across multiple lanes, allowing several neurons to be processed simultaneously while sharing control logic. Input data is accessed from packed vector by slicing out the relevant word based on current input index. Weight memory is accessed through flattened address, which allows a conceptually two-dimensional weight matrix to be stored in a single linear memory. Memory reads are explicitly staged to model synchronous behavior, with intermediate registers capturing weight magnitudes and sign information before accumulation begins. The arithmetic is split into magnitude and sign handling. Absolute values of inputs and weights are used for accumulation, while signed bits are combined separately to determine whether the accumulation result should be added or subtracted from the final sum. Bit serial multiplication is implemented by checking individual bits of the weight magnitude and conditionally adding a shifted version of the input magnitude. Partial sums are maintained per parallel lane and then merged into per neuron accumulators once all bits for the given input have been processed. Once all the inputs for the neurons have been accumulated, the engine transitions into a streaming phase. In this phase, the accumulated results are read from the internal storage and presented on the output interface one by one. A valid ready handshake is used so that the output timing is controlled by downstream pressure. Internal indices ensure that each neuron result is sent exactly once, and output validity is asserted only when data is stable and eligible for transfer. Finally, coming to the ReLU activation module, as we saw before, the timescale derivative sets simulation resolution and precision, after which ReLU activation module is declared with a single parameter ACCW that defines a bit width of all data paths, keeping the design scalable and consistent with the Mac engine output width. The port list follows a standard streaming style: clock and active low reset, defining the clock scheme. In data and invalid represent the incoming registered data and its validity. In ready is an output that advertises whether this module can accept new data, while out data, out valid, and out ready from the downstream handshake. Internally, the design uses explicit registers out data reg and out valid reg instead of driving outputs directly. This is a common system Verilog pattern that cleanly separates combinational handshaking from sequential storage, allowing the module to hold data stable across cycles if the next cycle applies back pressure. Then the in-ready signal is assigned using a simple combinational expression that depends only on the internal valid flag and the downstream readiness, meaning the module declares itself ready whenever it is not currently holding valid data or when the downstream has indicated it can consume the current output. The core sequential logic is implemented in a single always FF block, clocked on the rising edge, which enforces synthesizable flip-flop based behavior. On reset, both output registers are cleared, ensuring a known invalid state. In normal operation, updates to the output register are explicitly gated by out ready or not out valid reg, which guarantees the existing valid data is never overwritten unless it has been accepted or the register is empty. Within that condition, invalid controls whether new data is captured. If asserted, the ReLU operation is expressed as a concise conditional assignment that clamps negative values to 0 while passing non-negative values unchanged, and the valid reg flag is set. If no valid input is present in a cycle where module is free to update, the valid register is cleared, preventing stale data from being reasserted. Finally, continuous assignments connect the internal register to the module output, making the registered values externally visible without additional logic. The comments at the end clarify timing behavior rather than functionality, explicitly documenting the module introduces a single cycle registered latency, and the back pressure semantics are enforced by holding both data and value stable until out ready is asserted. The next step is to validate it through behavioral simulation, because this is where we prove that the logic we wrote actually behaves the way we intended, independent of hardware timing or placement effects. We have written standalone test benches for all the submodules to verify correct functionality. You can find all the codes uploaded in our GitHub repo. Let's start with the input buffer. So for the input buffer, simulation confirms that streaming inputs are correctly collected into a wide vector and the vector ready signal is properly generated. After reset, the right pointer and the internal buffer array are cleared, which you can see as zeroed signals in the waveform. When valid inputs data in and data invalid arrive, each value is stored sequentially in the internal array at the position indicated by the right pointer. The waveform shows pointer incrementing correctly with each captured input word. When the last element of the vector is marked by vector last and vector done, signal pulses high for exactly one cycle, indicating that the full input vector is assembled and ready for Mac engine. If vector last arrives early or the buffer fills without it, simulation clearly shows the pointer resetting and error messages triggering, which confirms the protocol violations are detected. Meanwhile, invec bus continuously reflects the packet contents of the buffer, and each slice corresponds exactly to the stored input word, proving that the generate based bus packing words intended. Additionally, when the downstream Mac engine signals busy, the waveform shows that data in is ignored and the pointer does not increment, demonstrating that back pressure is correctly handled and that no inputs are overwritten while the consumer is active. This ensures safe handoff of the full vectors to the next stage. Overall, the simulation validates the sequential logic, pointer-based control, vector packing, and back pressure behavior of the input buffer. For the wait memory, the simulation starts with the reset forcing the internal pipeline registers and read data to 0, which is visible as stable, inactive signals in the waveform. When enable is asserted, you can see the hidden index and input index being flattened into a single address one clock later, confirming the registered address pipeline. On the following cycle, the wait value appears at the correct BRAM location, while read shows a clean one cycle latency from R address to R data. When read and write occurs in adjacent cycles, the waveform shows no glitches, demonstrating that the registered write enable and address sequencing correctly protect BRAM timing. This confirms that the memory interface and its control timing are aligned with synchronous block RAM behavior. For the Mac engine, the behavioral simulation is more involved but very revealing. After reset, all accumulators, counters, and FSM states settle into idle and busy remains low. When start compute is asserted, the waveform shows a clean transition into the proc state, with busy going high and hidden and input counters beginning to advance. You can observe the wait memory read addresses incrementing in a structured pattern, matching the hidden by input traversal. While the internal wait signals introduce visible one cycle delay that model memory latency, during bit serial operation, bit IDX counter advances steadily and the partial accumulations update only when the corresponding wait bit is high, which is visible as stepwise growth in the partial sums. Once the last bit of the last input for the group of neurons is processed, the waveform shows FSM transition into stream, at which point accumulation stops and output handshaking begins. This confirms the control logic counters and FSM transitions are all synchronized correctly in simulation. For the output streaming phase of the Mac engine, the waveforms clearly demonstrate correct handshake behavior. When out valid is asserted, out data remains stable until out valid goes high, even if it takes multiple cycles. Each successful handshake increments the output index, and you can see the next hidden neuron's accumulated value being presented in order. When the final neuron is streamed, out valid deasserts and the FSM returns to idle, with busy dropping low, confirming clean completion and readiness for the next computation cycle. Now that we have covered all the modules and validated their behavior through simulation, it's time to look at resource utilization of our full design on a Xilinx RTX UltraScale Plus FPGA board. Our implemented network uses 256 input features, 128 hidden neurons, and a parallelization factor of 4. So the resource requirements reflect both the network size and degree of parallel computation. From the utilization report, we can see that the design uses 9391 LUTs, which is about 25% of the available LUT resource, and 9805 flip-flops, roughly 13% utilization. These resources are mainly consumed by the Mac engine, control FSMs, bit serial accumulation logic, address generation, input buffering, and the relay activation pipeline. The relatively low LUT and FF usage highlights the efficiency of the bit serial architecture, even with 4 parallel computation lanes. For on-chip memory, the design uses 15 block RAM tiles, corresponding to about 14% of the available BRAM resource. This BRAM usage is dominated by hidden layer weight memory, which stores 256 into 128 weight matrix, confirming that the large model parameters are efficiently mapped to dedicated memory blocks instead of LUTs. A key highlight of the DSP utilization is 0. Despite performing multiple multiply accumulate operations for the neural network, the bit serial computation approach completely avoids DSP slices, preserving all 216 DSPs on the device for other accelerators or future extensions. This clearly demonstrates the area efficiency and flexibility of the chosen architecture. In terms of I/O, about 97 bonded IOBs are used, which reflects the wide data path, control signals, and streaming interfaces required for integration and testing. Clocking resources are minimal, with only one global clock buffer in use, indicating a clean and simple clocking scheme. Now coming to the timing report, it shows that the design is timing clean and stable. The system is constrained to a 100 MHz clock with a 10 nanosecond period, and all user specific timing constraints are fully met after routing. The key metric here is the worst negative slack WNS, which is 0.987 nanosecond. A positive WNS means that the slowest path in the entire design still has almost 1 nanosecond of timing margin. So no setup violation exists. Correspondingly, the total negative slack is 0 nanosecond, and there are no zero failing endpoints across nearly 30,000 timing paths, confirming that the design meets timing globally. Hold time is also clean, with a worst hold slack of 0.002 nanosecond, indicating no hold violations. Because the design uses a single synchronous clock domain, the intra-clock timing table shows all paths are analyzed cleanly under the same clock, with no interclock or asynchronous timing issues. The absence of combinational loops, unconstrained paths, or missing clock definitions further confirm that control logic, Mac engine pipeline, memory interface, and streaming logic are all properly registered and constrained. Overall, the timing report validates one of the core design goals of the project. By using pipeline control logic and bit serial computation, the critical paths are kept short and predictable, even when 256 inputs, 128 hidden neurons, and 4 lane parallelism. The design comfortably meets 100 MHz clock target, leaving headroom for higher frequencies or future scaling. Finally, coming to the power report, it highlights one of the key strengths of our architecture: very low power consumption despite a reasonably large network configuration. The total on-chip power consumption is only 0.218 watt, which is extremely modest for an ultra-scale plus device. Out of this, 0.136 watt is static power, which comes from the FPGA fabric itself and is largely independent of the design, while the dynamic power is just 0.082 watt, directly attributable to our neural network computation. This already shows that the bit serial Mac approach is effective at keeping switching activity low compared to conventionally full parallel Mac designs. Looking at power breakdown, the Mac engine dominates dynamic power at about 0.037 watt, which is expected since it contains the core control FSM, bit serial accumulation logic, and parallel lanes. The input buffer 0.007 watt and hidden weight memory 0.008 watt consume relatively little power, confirming that buffering and PRAM based storage are energy efficient. CLV logic as a whole consumes around 0.015 watt and block RAM power is only 0.007 watt. Even though 15 BRAM36 blocks are used to store weights, importantly, DSP power is zero because design deliberately avoids DSP slices and instead relies on LUT based bit serial arithmetic, making the architecture portable and scalable. IO power is relatively higher at 0.027 watt, which makes sense because nearly 75% of the available IO pins are used, mainly due to AXI stream interfaces and control signals. Clock power remains low at 0.013 watt since the design uses a single 100 MHz clock domain with no PLLs or MMCMs. Thermally, the design is very safe. The estimated junction temperature is only 25.6 degrees centigrade, essentially ambient with maximum allowable ambient temperature close to 100 degrees centigrade. This means the design can comfortably operate without aggressive cooling, even in embedded or industrial environments. Finally, the report marks the overall confidence level as low, not because of any design issue, but because switching activity was not fully annotated using simulation generated activity files. With SAIF or VHD based activity backed annotations, the dynamic power estimate would become even more accurate. Even so, the results already demonstrate that our bit serial DSP free neural computation engine achieves excellent power efficiency, making it well suited for edge AI and FPGA based inference accelerators. To wrap up, I'd like to sincerely thank everyone for your time and attention and for staying with me through the architecture, code walkthrough, and simulation results and resource analysis. This project represents a practical exploration of efficient bit serial neural computation engine design on FPGA. And I hope it gave you useful insights on how such architectures can be built and optimized on real hardware. If you would like to explore the implementation in more detail, run the simulations yourself, or build upon this work, the complete source code, scripts, and reports are available on our GitHub repository, and we will add more with coming time. The link is provided here on the final slide. For any questions, discussions, or collaboration opportunities, you can also reach out to me at the email address shown on the slide. Once again, thank you for your attention, and I'll be happy to take any questions.